Hey, welcome to the problem solving session for organic chemistry. We're going to be focusing on the chapter 7 worksheet, which you can find in Canvas under the files section. This particular video is going to walk you through question number 1 of the worksheet, and there will be an additional couple of videos to walk you through questions 2 and question 3. I highly recommend that before you go through the video for this, that you attempt each of the problems on your own and try to get through as much of it as you can and use this as a way to verify your results and to help you in breaking through if you get stuck on any of the problems. So question number 1 to get started here. Some of the following examples show geometric isomerism, or you could also refer to this as configurational isomers, and some cannot. For ones that can, draw all the geometric isomers and assign the complete names using the EZ system. So we're given 3 different structure names here, starting with 3-bromo, 2-chloro, pent-2-ene. We'll start by drawing out that structure, and then we'll determine whether it's even possible for this to have EZ geometric isomers. If it is possible for it to have EZ geometric isomers, we're going to try to draw both of them and assign them each as E or Z. So looking at the name of this, the parent name pent-2-ene means that we need to have a 5-carbon chain with the carbon-carbon double bond of that alkene between carbon number 2 and carbon number 3. So I'm just going to draw out a 5-carbon zigzag line here to start with. And that has turned out to be 6 carbons, so I delete 1 there. And between carbons 2 and 3, we're going to put in our double bond. And then at position 2, there's a chloro atom, so I'm going to plug in the chlorine there. At position 3, bromo, so we'll put in the bromine there. And then we ask ourselves, is it possible for this to exist as E and Z geometric isomers? The way that you can evaluate that is you look at each individual carbon of the alkene group, so the carbon atom here on the left that I've dotted in red, and you ask yourself, does that have 2 different groups attached to it? It definitely does. It has a chlorine and a methyl group. And then you do the same thing at the other carbon of the alkene over here that has a bromine and an ethyl. That's 2 different groups. So if there are 2 different groups at each of those individual carbons, that will mean that E and Z configurational isomers are possible. So let's go ahead then and assign the particular isomer that we've drawn here as E or Z. And in order to do that, what you will do is you look at the carbon on the left, we'll start with here, the one that's outlined in red, and you ask yourself, which of the 2 groups that is directly bonded to that carbon is higher ranking, chlorine or methyl? And remember that we determine rank based on the atomic number of the atom that is directly connected to that alkene carbon. So chlorine has a higher atomic number if you look at your product table than the carbon that is attached here as part of the methyl group. And so higher ranking group there is chlorine. So I'm just going to circle it to remind myself that that is the higher ranking group attached to the carbon on the left, the carbon that's outlined in red highlight there. On the right, we have our green highlighted carbon atom that's directly bonded to a bromine and to an ethyl group. The higher ranked group on that carbon is going to be the bromine, because bromine has a higher atomic number than the carbon that is directly connected up here. So looking at that and recognizing that those 2 higher ranked groups, the chlorine and the bromine, are on opposite faces of the molecule, indicates to us that the configuration of this would be assigned as E. E means that the higher ranked groups are on opposite faces. Opposite faces means that if you look relative to the carbon atom of the alkene, one of those groups that's higher ranking we would go up to get to. The other one we go the opposite direction, in this case down to get to. So the higher ranked groups therefore are on opposite faces of the molecule. To draw the diastereomer of this, or in other words the Z geometric isomer, we need to make sure that those two higher ranked groups are on the same face of the molecule. So I'm going to go ahead and redraw my 5-carbon chain, and this time I'm going to draw it in such a way that my chlorine and bromine end up on the same face of the molecule. So you have to change the orientation of the alkene group carbon chain there a bit in order for this to work out. So we have our 5-carbon chain, and then we're going to plug our chlorine atom in at carbon 2, bromine in at carbon 3, and now you will notice that our two higher ranking groups, that is our higher ranking group that's bonded to the carbon in red on the left, is oriented upward, and looking at the carbon on the right of the alkene, the higher ranked group there is also pointed upward. So now the two higher ranking groups are on the same face of the molecule, and so that indicates that this is going to be the Z geometric isomer. So let's go ahead and do this same sort of thing for the next problem, penta-1,3-diene, and using the same approach that I did in part A, what I'm going to do is draw a 5-carbon chain, just drawing my typical zigzaggy line, and then our name here, 1,3-diene, 1 indicates that there's an alkene group starting at carbon 1 of the chain, 3 indicates there also has to be an alkene group starting at carbon 3 of the chain. So there's our penta-1,3-diene, and we have to ask, are geometric isomers possible for this? And we have 2 alkene groups here, so we have 2 places where we can look and ask ourselves, are geometric isomers possible there? As we saw in part A, for a geometric isomer to be possible at a particular alkene group, the alkene must have each carbon atom of the alkene with 2 different groups bonded to it. So this alkene group that's at the terminal end here, that I've outlined the 2 carbon atoms in red for, at position 1, there would have to be 2 hydrogens directly bonded there. That means that 2 of the groups, those 2 groups, are identical, and therefore this is not a stereocenter, meaning there's not going to be geometric isomerism at that alkene group that starts at position 1. So on the other hand, if we hop over to the alkene group position 3, which I'll outline in green here, are 2 carbon atoms. At position 3, we have a hydrogen implied there, and therefore at position 3 there are 2 different groups bonded because we have a hydrogen going here, and going to the left there's a carbon atom. At position 4 there's also 2 different groups there because you'd have a hydrogen, and then you also have the methyl group out here at the end. So that particular alkene group is a stereocenter because it has 2 different groups bonded at each of the carbon atoms. And so we can assign that particular location as E or Z. And to do that, we do the same thing that we did up top. We look at each individual carbon atom. So I'll start with the carbon atom here at position 4. Ask which of the 2 groups directly bonded to that is higher ranking. It's going to be the methyl group because it has a carbon directly bonded rather than going upward. We see a hydrogen there. At position 3, we have a hydrogen directly bonded, and we also have this carbon atom over here that's part of the other alkene group bonded there. And so that's the higher ranking group at carbon number 3. So the 2 higher ranking groups then go in opposite directions, one going up like so, relative to the carbon it's bonded to, the other going down relative to the alkene group carbon it's bonded to. And so therefore, this is going to have the E configuration. The higher ranked groups are on opposite faces of the molecule. We can then draw the diastereomer of this, the other geometric isomer, that is the Z configuration. And we will do that by adjusting the orientation of our bond here. So I've drawn positions 1 through 4 of the chain the same as in the E configuration. When I get toward position 5, carbon number 5, rather than orienting that downward, I'm going to bring it up like this so that we have drawn the Z configuration. And we can recognize this as the Z configuration because if we think about what is the higher ranked group that's bonded to carbon number 4 here, it's going to be that methyl group that I've put a circle on. If we look at carbon number 3 and we ask which is the higher ranked group there, it is going to be headed back toward carbon number 2. So both of those orient in the same direction. They're both up relative to the carbon atom that they're bonded to, and therefore this molecule is in fact Z. And I'll just clean that up a little bit because I've got some circles going on there that make it a little crowded looking. But that is going to be your Z configuration there. So then on to the last part of this problem. We have 3-ethyl 5-methyl-oct-3-ene. So we'll go ahead and draw out that structure. Need to draw an 8-carbon chain here. So making sure I've got 8 carbons in my chain. I think I'm going to need to add 1 or 2 here. Have 7 carbons at the moment. Bring in that 8th carbon. Oct3-ene. The 3 there means that the carbon-carbon double bond starts at carbon number 3, so we plug that in. Position 5 is our methyl group, so we'll plug that in like so. And position 3, we need to put an ethyl group in there like that. And then you are asked to indicate whether it can show geometric isomers or not. So we will start by looking at the carbon atom on the left here of our alkene group. And you have to ask yourself, does that carbon have 2 different groups bonded to it? So looking at that, it has 2 identical groups bonded to it, not 2 different groups. So it has an ethyl group here, ethyl group here. Anytime you have a single carbon atom of that alkene that has 2 identical groups, it means there are going to be no geometric isomers, no stereoisomers for that. You will note, perhaps in this molecule, if you're taking a close look at this and thinking about other types of stereoisomers, such as the RS configurations, there is a chiral center here at position 5, but that's irrelevant to this question because the question is specifically asking about geometric isomers that are E and Z, and you never have EZ stereoisomers at a tetrahedral carbon like this one. That would instead be RS type stereoisomers because you have 4 different groups bonded to a single carbon there rather than it being an alkene. EZ is specific to alkene configurational isomers. So with that, we conclude question number 1 of our problem solving session. Stay tuned for the next couple of videos to walk you through additional problems that relate to geometric isomers and relate to elimination reactions.